Hello, my name is Uwe Artmann. I'm the CTO of Image Engineering. In this webinar, I would like to talk about how you can improve the efficiency of geometric calibration. So let's jump in. So what are we going to talk about today? So what is geometric calibration and why do we need that? So for most of you that might be already clear, but we would like to show you on one side how to perform a geometric calibration in a very efficient and great way using the GEOCAL. And then I will summarize for you why we think GEOCAL is a very efficient way to measure the geometric calibration. So when you perform a geometric calibration, you identify all parameters that you need for a model to calculate from the image coordinates into world coordinates. So we have here as an example the simple pinhole model that is used also in OpenCV that is commonly used in the industry, but there's many out there. So with our product we support many different models, but we use that here as an example. So if you have the model and have all parameters of the model, you know where camera is in respect to the world coordinates, and you know what is the meaning of the pixel coordinates so that you understand what does this mean in the real world. So the geometric calibration is technically a bunch of variables into an equation system. And if you have all these variables, you can calculate from the point in the image, which is two-dimensional, into the world coordinates. For that, you need different parameters. For example, here, the camera intrinsic matrix that contains the focal length in pixel and the principal point. Additionally, you need the extrinsic parameters that contains rotation and translation of the camera in respect to the world coordinates. So if you have these, you can feed that into your equation, as a matrix into your system. So if we have all that, we can go calculate back and forth, but something that we also have to consider is the distortion. Distortion is a change of the reproduction scale over field. So that means a lens distortion will have an impact of what the meaning is of a single point. So we need to characterize the distortion very precisely. And this is something that we also do in the geometric calibration to define the different distortion that you can have. The radial distortion is, I think, the biggest contributor, but we also have tangential distortion and other forms that contribute to shifts or to pixel coordinates that they change over the field position, so from the center to the corner. If we have all these parameters well measured and have them in our model, we can correct for the distortion. So with the model, and this is an example, but technically that works with all different kind of models, we can calculate from the image coordinates into world coordinates and use that data for our application. So why should I do it? Yeah. Well, as I explained, when we have our geometric model, we also understand the exact distortion of the device. So we can then also use that to undistort an image or to unwarp, or however you would like to call that. So with the strong distortion of the lens, we can correct that very properly when we have all parameters of a geometric model. But that is even more important in many cases is with all this information, you can also measure distances in the image and say that is a certain distance in the object space. So if you need to know how far an object is or how wide a certain object is, regardless if it is in the image center or in the image corner, for that you need the geometric calibration. So in robotics or in automotive application, wherever you have cameras that are sensors for your system, and especially when it's safety relevant, geometric calibration is very important. So how do we perform geometric calibration? There are different ways to do that, but one very commonly used one is what we call the checkerboard dance. So you have a target that shows a certain pattern The most popular one is this checkerboard, and you capture many images with the same target in slightly different positions around the camera. So you change the location slightly, you change the angle towards the camera. So with all these images, you can then perform the geometric calibration. So if you rotate the chart, or like in the lower right, that is an example where a car is rotated and many charts are placed around that. But it's the same idea. You have many images, many times you have this chart to use that for your calibration. Another approach is, because this checkerboard approach where you need a lot of images is something that is very hard to do on a production line. I mean, you need to position all that, so that's maybe for the lab, but for a production line it might be harder, or you don't want to capture multiple images. So there are approaches, and mathematically you can also do that, so that you have a very precise alignment of your camera towards a very precisely positioned and measured target. So that way you don't need multiple images. You can have one image where you have for each point that you can measure in the image, you have the corresponding coordinate in the world, and with that you can also solve the equation system. But as said, that has a very high demand on the alignment process and on the mechanical setup. So something difficult. What all chart approaches have in common is that we need to have the chart in the focal plane. So if your camera is focused and fixed focus to several meters distance, or even to infinity, you need a very large target. And that can be done in the lab. So you have, I don't know, a square meter of test target, you can rotate it around. But if you think about production line, that's really a problem, because then you get a huge footprint. Your machine or whatever automation you have to do that gets quite large, and that can be a problem. Also, if you have then a different setup in the lab than you have on a production line, you always need to make sure that that is the same. So you cannot use the same approach in the lab than in the production line, which is then critical because it makes a huge offset in your development until you reach the state that you have a smoothly running production line. So we have a great solution for that. That's called GEOCAL. So I hand over to Kai, my colleague, who will show you the performance and the possibility how to measure the geometric calibration with GEOCAL.
Hello and welcome. I would like to give you a short demonstration of a geometric calibration with GEOCAL. The GEOCAL has a unique ability to generate a regular grid of light spots starting from infinity. This allows you to accurately measure the geometric distortion, focal length and focal point of your camera. Let's take a quick look at the technology behind it. The laser diode produces a beam that is first expanded and then collimated into parallel beams that pass through the diffractive optical element to form a precise grid of light spots. The camera under test captures this grid. The data collected is used to calibrate the camera's optical parameters, ensuring high accuracy and performance in imaging applications. So how do we perform a calibration with the GEOCAL? The setup is very simple, as you can see here. We need a stable table or mount for the GEOCAL. We need a tripod and mount for the camera and a tripod head to control the rotation of the camera. This camera is a regular industrial camera with a field of view of approximately 60 degrees and HD resolution. The camera is connected to this PC. Now let's start with aligning the camera. Since the light spots are coming from infinity, we can get very close to the DOT. First, we place the lens so that it is approximately in the center of the opening. If you have a water level, you can also use it to balance the camera. However, a slight rotation of the camera towards the DOE is not a problem. From here, we can fine-tune the alignment. Check that the brightest spot, the 0th order, is in the center. A grid overlay of the image is very helpful. Now that the brightest spot is in the center of the image, we do the horizontal alignment of the camera, and that's it. Before we take a picture, we should check the focus again. The grid points should be sharp in the image. The calibration will work best if your camera can focus to infinity. We already adjusted the exposure of our camera so that the dots are not saturated. It is okay if the image looks dark. Also, there should not be a lot of image processing be involved for the dot detection to work well. Now we are ready to take an image. Alright, let's get some results from the image we just captured in the GEOCAL software. First, we need to load a configuration file. There's several configuration files available for different distortion models and different versions of the GEOCAL, which you can then use for your own customized configuration. Let's take the default configuration even brown for now. And now we add the image we just captured. Here we go. And there's just two steps you need to do for the analysis. First, you need to detect the points in the center. That's what the software uses to calculate the reference grid. The reference grid is, so to say, the undistorted grid, so the grid where the points actually should be. And now we can do the analysis. So that's it. That took about 2 to 3 seconds. And if we click on Show Grid, we can see that the detection or the analysis worked quite well because most of the points in the image have been detected. In the image viewer, we can also see the reprojected grid. So if we just zoom in a bit, then we will see that there is an overlay on the point of magenta pixels and green pixels. So the green pixel actually represents the detected grid, the center of the point which has been detected. And the magenta pixel represents the reprojected grid, which is based on the intrinsic camera matrix and the distortion coefficients which we just calculated. In the Result Table tab, we can see the numerical results. So the ones you need to undistort your image are the focal length in X and Y direction, the principal point, U and V, and you need the distortion coefficients. In this case, it's 6 distortion coefficients because we defined that in the configuration file. Another important parameter is the RMSE value. That's the root mean square error of the distance in pixel between the reprojected grid and the detected grid. The lower this value, the better. So in this case, it's 0.35 pixels, which is actually a pretty good result. In the other tabs, we show the distortion curve. For example, this distortion curve is based on the local geometric distortion. If you need more information about local geometric distortion, please visit our home page. And another useful visualization is the 2D color scatter plot, which shows a heat map of the distance between the reprojected grid and the detected grid. So this is quite good to see if the reprojection actually worked well over the entire image field, or if there are special areas, for example in the corners, which didn't work that well. And the histogram finally just shows you how many points were detected in the image depending on the radius and depending on the angle. But as we already saw here in the viewer, we have a good result here. So that's all we need, and now we can save the result as an XML file or CSV file for further processing.
Thanks, Kai, for taking over. So, to summarize, why do we use GEOCAL, or why do we think GEOCAL is a great solution for your application? So, if you compare the different methods, how to perform that, GEOCAL, you just need a single image. So, the calibration process can be significantly simplified due to this novel approach we use in GEOCAL. Also, because of the focus distance that you need large targets, so you need huge machines. So it doesn't have to be a machine like that, but typically this is always a significant footprint. So these are significant machines with a huge size. And GEOCAL is very small. And if you take it upside down, your footprint on the floor is really minimal. And as you know, on production lines, the footprint is that what really costs money for place, and all associated costs. So you really would like to have such machine as small as possible. With GEOCAL, that's possible as we project from infinity in a small setup. So that's great and extremely useful. Also, the requirement for your mechanical setup is minimal. So you need to place the camera, the DOT, in front of the GEOCAL. Yes, but the requirements for how precisely do you need to do that are easily achievable. So they are so easy that you can also do that by hand in the lab. So there is no need or no requirement that there's a difference between the lab and the production line. So that's always what you would like to have. So you can do everything in the lab, you validate the system, you know the results, you can easily check a single individual device, and then you go in production line, you do exactly the same thing, so you don't have to start again. So extremely powerful for GEOCAL. We know, and I talked about that, when you use a target, that you need a large, huge distance, a large target, because of the focus distance. So there's one idea out there to use relay lenses. And yes, so you have your device on a test, you put a relay lens in front of it, and that makes, you can use, instead of a large chart, you use a smaller chart. That does work, but you need to invest a lot of time and resources into the additional development and validation of that relay lens and of the whole process. And that even increases the requirement for all the alignment, because you need to align the camera very carefully, you need to align the relay lens very carefully, the chart. So that is really a problem. So with GEOCAL, you have no relay lens or any other optical component is needed. So optical production line changeover is so much easier and faster. So each time you want to change your production line, if you have the traditional way, you need to invest a lot of time into aligning, into validation again, and so on and so on. With GEOCAL, it's extremely easy, as you have no specific requirements or optical components or mechanical components. You just need to be able to place another kind of camera in front of GEOCAL. Everything else is then done in software. The hardware stays the same. So you can, if you want to have a high efficient production line and have quick changeover from one product or one version to another, with GEOCAL, that's definitely possible. And you could switch very quickly between that, as everything done is in software and no optical components specifically for your project. That makes the geometric calibration so easy that there's no excuse why not to do an individual calibration per device. I know there's production lines where you go with non-individual calibration. You just check somehow the distortion and then you take class calibration data. There's no need for that with GEOCAL. So you can do an individual calibration, and with that you already improve significantly on your production line, as you can individually calibrate your camera. You can have individual coefficients for your camera. And with that, you increase the precision of your entire line or of your product. So to summarize, we have a method to measure the geometric calibration from infinity with GEOCAL in a very small footprint. That comes with a high precision so that you can really measure it at least if not over comparison with other methods. So we have seen customers using it right away because they were so fascinated for the precision that they could use it right away. The development time is reduced significantly. As you don't need to develop specific optical component, you don't need an additional task for all the validation and alignment of new optical component as soon as you change over your production line. You can just use the GEOCAL for different kind of devices. It's fast. So the analysis, you just take a single image and then you put it, provide it to the API that we can provide with the hardware, and then you can quickly get your geometric calibration. As you just have a single image, also the transfer is easy, and no relay lens needed, no individual optical component. So you can also cross that out from all the costs that you have in the entire project to develop a camera and to bring a camera into real world. So you have seen all the benefits of GEOCAL now. I'm sure it can be great help in your project. Thanks for watching and see you soon.